Welcome. Welcome to the method of joints, one of the very powerful methods to solve for a truss. The method of joints, right? It's an analytical technique used to solve for the member forces in a simple truss. And it just comes from the fact that if the truss is in equilibrium, right, then every joint in the truss must also be in equilibrium. Every joint in the truss must be also in equilibrium. And this gives you the hint of what the method of joints is, right? We are going to isolate each joint. We're going to apply the equations of equilibrium at the joint. Careful, we have only two available. Sum of forces in x, sum of forces in y, both of them equal to 0. We cannot use moments because the joints don't develop any moment, so any moment equation will be meaningless. Right? There is no moment arm. If you isolate one joint, right? If you isolate one joint, what you see is only, right? All the forces coming to the joint, right? Have 0 moment arms, right? So it's meaningless to use moments. And then, right, solving for the member forces at the joint. Now, if you have two equations of equilibrium, right, two equations of equilibrium at the joints, how many unknowns can you solve at each joint? So, two equations of equilibrium at the joints, at each joint, and you're going to be using each joint separately. So that means that you can only solve for two unknowns at each joint. Don't worry, right? Don't worry, that is not a concern. There will be always a joint in which you can apply your method. So the method is draw a free body diagram for the entire truss and solve for the support reactions, right? Now that you have become experts at calculating the reactions in rigid bodies, right? The first step is to calculate the reactions for the truss. Now, once you have the reaction forces, right, we're going to explode the truss. This means separating members from joints, right? Members from joints. So we can isolate the joint later, right? So we explode the connections, right? Explode the connections. We draw a free body diagram at each joint, right? At each joint. And then, right, each of these members will give me a force coming to the node. And then once I have all these forces, right, I have to take note of my unknowns. Well, the known forces and the unknown forces, right? And then apply my two equations of equilibrium at each joint and solve for the member forces. So sum of forces in x equal to 0 and sum of forces in y equal to 0, right? Those are my conditions for equilibrium, right? I cannot solve if in a given joint, in a given joint I have 3 unknowns, right? If I only have these two equations, right, I need another one, and then I won't have it because I am just investigating the equilibrium of the joint, right? I cannot use another part of the truss to solve for that one, right? So I have to move to another joint until I find one that has 2 unknowns, right? No more than 2 unknowns, right? So let's take a look at the method step by step with a simple example. I have a truss, right? And it says that I have to draw a free body diagram for the entire truss, right? And solve for the support reactions, right? So solving for the reactions is actually the first step. Now, when I solve for the reactions, I am allowed, right? Because it's for the entire truss. So there are moments inside the truss, right? So when I solve for the reactions, and I am dealing with the whole truss, I have my 3 equations for equilibrium. right? So you may say, hey, what happened, right? So when you have the whole truss, you can use the three equations of equilibrium, but when you are investigating a node or joint, I have only two, right? That's right, right? That's right. I can use moments for the whole truss because the parts of the truss, right, and the reactions, they cause moment, right? The only part in which I cannot have moment is at the joint, right, at the given joint. So I have this this situation. Let me just erase this part. Erase this part. So it doesn't actually. sorry. So let me actually proceed with calculation of the reactions, right? So I have two nodes, right? And then you see this is a pin at node A. It's a pin. So I have two reactions, right? One reaction in Y and one reaction in X. And in the other side in B, I have a roller. So I have only one vertical reaction. So I have three reactions and three equilibrium equations. So I can solve for the reactions. So first equation of equilibrium, sum of force in X equal to 0. Everything going to the right is equal to, is positive. So the only force going to the right, and the only actually horizontal force, is the reaction at X, which is equal to 0 directly, right? The next equation is sum of forces in Y is equal to 0. So I have force in the reaction at A in Y plus the reaction at B in Y minus all the forces in Y. So I have minus 100 equal to 0, right? I have two equations, one unknown. I need another equation, which could be moments. Where should I calculate moments about? What is a good place to calculate moments? So I take a look at node A and I see two reactions there. So if I calculate moments about that node, I'm going to eliminate those two reactions. So I actually do that. Sum of forces at A equal to 0, counterclockwise is positive. So I'm going to get, right, this 100 force creates clockwise moment. So it is 100 times 2.5, right, negative, plus, right, the reaction at B in Y, right, times this moment arm, which is 6 meters. So it's, and it creates counterclockwise moment. So it's positive 6 times 6 meters times RVY equal to 0. So from this equation, I can solve for RVY, and I get 42 kilonewtons in this case. And going to this equation, I can solve for the reaction at A in the Y direction equal to 58 kilonewtons. So far, nothing strange. I have calculated my reactions. When I have the whole truss, I can apply three equilibrium equations, right? So we don't forget three equations of equilibrium for the whole truss. For the whole truss, right? So the next step is to explode the truss. We separate joints from members, and that's what I have done in this case. And I have also kept my reactions, right? This guy is 42, and this guy is 58. And in the top, we have the force of 100 kilonewtons. Now, I have to draw a free body diagram at each joint, right? A free body diagram. So this means that I have to assume forces, right? Forces actually coming to the node from each member, right? So, right, I have to come up with the forces that this member is, for example, this member, the forces that this member is actually exerting on the nodes. So, would the force be towards the node? Would the force be, actually, this was not very clear. is the force actually coming towards the node? Or is the force actually, for example, for this member, is the force actually coming towards the member, right? We have to make those decisions, right? We have to make those decisions. Now, one technique, right? Because we don't know the forces. If we knew the forces, there is no way, there is no need of solving this truss, right? So, one very nice technique about this, right, is, for example, assume tension all the time, or assume compression for all the trusses, right? Now, the next problem is how to actually represent tension, right? So let's just start with some assumed senses on the forces, right? Don't worry if they represent tension or compression, right? I'm just going to write some arrows, right, which assume that the members are either in tension or compression, right? Don't worry too much about why is the arrow going to the node or coming from the node, right? So what about this? In this member, right, this member here, I'm going to assume that the arrows actually go towards the nodes, right? And what about this other member? The same thing. It's kind of fairly symmetric. So I'm going to assume that for this member, right, the forces that appear at the node, right, actually have that orientation. And for this member, right, for this bottom member, I'm going to assume that the forces are reversed, and actually the forces go towards the member, right, from the node towards the member. Now the question, right, the question that you're figuring out, right, the question that you are wondering, so is this element in tension or compression? Now, if you are like me, right, I see this figure, and I see these forces, I automatically assume that this is in tension. Now take a look, take a closer look. There is a member over there, but the force, right, is away from the. It's not actually, right. It's not created by the member, right. It's a force in the node. It's not even touching the member. So, is it still tension, or is it compression? Right. Now, if the forces were like this, right, it will be easy to assume that it is tension, right? But take a look, the forces in my figure, right, these forces that I drew, right, the green forces, they are at the node, they are not at the member, right? So let's take a look, right? It's important to notice that we are drawing the forces in the nodes, not in the element, right? Not in the element. Not in the element. Right? So if we actually wanted to find the forces in the element, right, we have to think about this, right? We have to think about that the element must be in equilibrium with itself, right? Equilibrium must exist in the member itself. So, right, if I have these forces acting on the nodes, to equilibrate those forces, right, these forces should apply, right? We are equilibrating here at the interface, right? Right at the end of the member, there has to be equilibrium. So the red force appears, and that red force, my friends, is actually touching the element. So, right? So the red forces tell me that this element is in compression, right? The green forces were acting at the nodes, but the red forces, they act at the member, right? So the element is in compression. What about this situation in which the node forces actually go towards the member? Well, if I have to equilibrate the interface of my member, right, the red forces, which are forces at the member, appear like this. And these forces are pulling, right, are pulling from my member. This is, of course, tension, right? Yeah, the element is in tension, right? Now, let's keep this in mind. Now, let's go back to our drawing. So, same question, right? Same question. What is the force in this element, right? We have to remember. Well, it appears to be, right? It appears to be these tension forces, right? Let's actually do it for the one that is going to appear, right? So the node forces are like this, which means that the member forces are like this. And this element is in compression. Right? The same for this other member, right? Compression for this guy. And what about this guy? Well, forces in the member are like this, right? So this element is the only one in tension, right? So this is one of the kind of the finer things, right? The finer things. People is usually very, very good at applying the equilibrium equations and to balance each node, but sometimes, right, we don't pay enough attention to what the members are feeling, right? So in the method of joints, right, it's important to remember that we are drawing 3 body diagrams at each joint, and wherever forces arrive to a node, wherever forces, right, are forces in the node, and the element that arrives to the node actually has opposite forces, right, coming in, right, opposite forces. So opposite forces. Since the member has to be in equilibrium with itself, it develops this other force in the other side, right? And then based on the red forces, this guy is in compression. This guy is in compression. And this guy is in tension, right? So don't decide on if the forces or if the elements are going to be in tension or compression based on the nodal forces, right? Always do this exercise of trying to figure out what is happening with the member. Now that we have proposed some forces in the joints, right? We have come up with the green forces, and you can assume whatever you want, right? Nothing will happen. If the element was not in compression, but you assumed compression, and put your green arrows like this for compression, but the element was in tension, don't worry. All that you'll get is your forces in a negative sign, and you can fix them later, right? So don't worry about that. So the next step is actually to apply the equations of equilibrium to each joint, right? The equations of equilibrium at each of the joints, right? And then based on the forces that you get in the joint, right? Then you decide what forces are in the members, right? And then you have to present the answer, which means that you have to prepare a table that says member, right, 1, 2, 3, 4, A to B, right, B to C, C to D, E to D, or whatever, right? And then how much force, and if it is tension or compression, right? So 500 kilonewtons tension, 400 kilonewtons compression, 300 kilonewtons compression, 800 kilonewtons tension, right? Something like this. So that's the solution of a truss, right? Telling if a certain element is in tension or compression. So I have an example for you, right? And a very nice truss, right? A very nice truss. It has a pin over here, so 2 reactions. It has a roller over there, so 1 more reaction, which means 3 reactions. And how many equilibrium equations? For the whole truss you have 3, so 3 equations, 3 unknowns, so you can get the reactions easily, right? And then this truss has, let me show you, right? Let me show you 3 forces, right? 1 force over here, another force over here, and then 1 force over there, another force over here. So four forces, right? 4 forces. Is this a simple truss, or is it unstable, or is it statically indeterminate, right? So we apply the equation, which is 2 times n minus m. N is the number of joints, and m is the number of elements or bars, right? So we apply the equation, right? We have 8 joints, right? 8 joints 1, 2, 3, 4, 5, 6, 7, 8 joints. How many members? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 members, right? 8 joints, 13 members. We apply the equation and we obtain that is equal to 3. So we have what we call a simple truss, or more technically, a statically indeterminate truss, which means that the equations of equilibrium are sufficient to obtain these forces, right? So I'm going to redraw my truss over there, right? And then the first step is to calculate the reactions. So I have 2 reactions at node A, right? And 1 reaction at node E. Remember, to calculate reactions, I can use the 3 equilibrium equation, right? So I apply sum of forces in x equal to 0, right? Which means that I have the reaction at A, right, minus 5 equal to 0. That means that the reaction at A in x is equal to 5. So one reaction, 2 more to go. Sum of forces in y equal to 0. Whatever is going up is positive. So I have 1 reaction at A in y, right, positive, plus the reaction at E in y, positive as well. Minus 10, minus 10, minus 5, right, equal to 0. One equation, 2 unknowns. I cannot solve for the reactions yet. And then I need an equation of moments, right? I can apply moments. Where would you want to apply moments? What about point or node A, since we can get rid of 2 reactions at once? So applying moments, right? This is a simplification of this equation over here. Applying moments at A counterclockwise is positive, right? I have minus 3, right? Let me use, what about red color for the moments? Green color for the moments. So I have this one, this force, which applies clockwise moment. So it's 10 times 3 negative, right? And I have this force which applies clockwise moment. And so it is 10 times 3 plus 3 meters, so 6 meters, minus 10 times 6, right? And then what about this force over here? So it's 5, also a clockwise moment, so 5 times 6, negative. What about these 5 kilonewtons over here? So this guy actually produces counterclockwise rotation at point A, so it's positive 5 times the moment arm, which is 3 meters. 3 meters, so 5 times 3. And then the reaction at E, right? So this guy creates counterclockwise rotation about A, and it is spaced 3, 6, 9, 12 meters apart, right? Equal to 0. And from that equation is one equation, one unknown, I can find the reaction at E in y equal to 8.75, and I can come back to this equation and find that the reaction at A is equal to 16.25 newtons, right? It's up to you to do it on your own, just to check that we are able to calculate reactions, right? It's very important to always check that, right? And then the next step is to solve joint by joint, right? Explode the truss and then go joint by joint, right? So we can choose any joint we want, right? We are going to choose a joint with 2 unknowns only, because I have 2 equations of equilibrium only. So what about we start with joint A? Okay, joint A. And remember, we are illustrating forces that arrive to the node. Here are my reactions, right? Here are my reactions, right? They arrive directly to the node. No need to think anything about that. And then I have my FAB force, right? My FAB force. I'm assuming it actually moves away from the node. It's an assumption at this point. Right? It's an assumption at this point. A preference of mine is to, when I'm equilibrating nodes, right, I always assume that my forces stick out from the node. I don't know why, right? But I always assume that sense on my arrows. So force AF, right? That diagonal force, it's also sticking out from the node at 45 degrees. 45 degrees because these angles are 3 meters and 3 meters. And then I have two unknowns, right? 1 and 2. And I have two equilibrium equations I could use to solve for that, for those forces. So I apply sum of forces in x equal to 0. Whatever moves to the right is positive, right? I'm just looking at this joint, right? I don't have to look at any other point in the truss. Okay, so I have 5, right? I have 5. So let me just circle in red, right? So 5 plus FAB, right? 5 plus FAB plus, right, the horizontal component of force FA, right? AF, right? Sorry. So the horizontal component is equal to, right, FAF cosine of 45 degrees, right? So FAF cosine of 45 degrees equal to 0. I have one equation, two unknowns. I have to wait for the next equation. So sum of forces in y equal to 0, but all the forces in y. So I have 16.25, my first force, right? And then the vertical component of force FAF. So this is FAF sine of 45 degrees. So FAF sine of 45 degrees equal to 0. So this is one equation, right? One unknown, FAF equal to minus 23, right? Minus 23 means that force FAF actually comes to the node, right? I assumed wrong. I don't have to go back and do anything, right? I just need to write or to change the sign here in the drawing, but I don't do anything on the calculation, right? And I use the negative number on this equation, right? I don't change it, right? It came out negative. On the equations, I don't do anything. So once I plug that number into that equation, I get that FAB is 11.3 positive, right? FAB, which means that FAB, right? FAB has this right sign, right? So the next step is to place these forces on the drawing, right? Place these forces on the drawing. So here are my corrected forces. You see how FAF is actually coming, right? I'm talking about node A, right? Right, node A. So you can see how force FAF has its corrected sign, and force FAB actually moves away from the node, right? Away from the node. And then I know that the opposite forces are going to be created on the other side of the member, right? So this is key. I know that an opposite force is going to be created on the other node. So I go ahead and transmit the forces into the next nodes, right? And then the next step is to actually draw the forces in the member, right? Well, if we have to equilibrate the member, right, these are the directions of each force. And then this member is in compression, the one in the top in green, and this member is in tension, right? This member is in tension. So let me just erase here so it makes it clear, right? So you can see how, right? You can see how we were careful in our nodal forces, and then now we can very clearly see which elements are in tension and compression, right? Again, the forces we draw at the joints, these are not the forces we use to know if it's compression or tension. We have to draw the forces at the members, right? The forces at the members. The next step, right, is just to put numerical values, right? Numerical values. And then, for example, I put the 23 right at node F and 11.3 at node B. And the next step is to choose what is the next joint to be analyzed, right? We have we have a bit of a few options, right? A few options. So what about we choose node F? How many unknowns at node F? I have one element that I don't know the force on, another element that I don't know the force on, and then three elements. How many equations of equilibrium? Two, right? So I cannot go to node F just yet, right? What about I go to node B? At node B, I have two members, right? I have two members that I don't know the forces about, right? So this element and this element, right? I don't know them. So I have two unknowns and two equations of equilibrium. So the most logical choice is node B to follow, to continue with the process of finding reactions, right? So node B, right, appears to be like this. And again, right, remember, I'm assuming the senses of the forces. So remember, I always draw my forces sticking out from the node, right? From the node. So I have it like this. So I apply my equilibrium, sum of forces in y equal to 0. My only force is FBF, which is equal to 0, right? So yeah, members can have 0 forces, right? In this case, member BF has 0 force, right? And then I apply sum of force in x equal to 0, FBC positive minus 11.3, so that FBC is 11.3 kilonewtons. So I put a numerical value. For the forces in the two members, and now I can direct my attention to node F, right? Since now I have two unknowns only, right? Because member FB is carrying 0 force. I have only two unknown forces. So equilibrium at joint F, right? And at joint F, again, right, I assume that my forces are sticking out, and you see how I draw force F, FG sticking out, and force, unknown force, FFC sticking out like this, right? And I proceed to do equilibrium. So two unknowns, two equations of equilibrium. So sum of force in x equal to 0, right? So I have right, 23 cosine of 45 positive, and I'm talking about this guy, right? This guy is 23 cosine of 45 degrees positive. That's a component of 23. Plus FFC, right? It's this guy. It's the horizontal component of FFC, right? So let me just write it here. Here. This is FFC cosine of 45 plus FFG, right? So this guy over here, right? Equal to 0. So I have one equation, two unknowns. I have to wait for the next equation. So sum of force in y equal to 0, right? So I forget the sign convention here, right? Sum of force in y equal to 0. So I have 23 sine of 45 degrees, right? This is 23 sine of 45 degrees positive, right? Minus FFC, right? Because this component of this force goes negative. FFC sine of 45 going negative, right? FFG doesn't have vertical component, and minus 10, right? Minus 10. And then I have one equation, one unknown, FFC equal to 886, and FFG is minus 22.53. FFG here, FFG is actually going to the left, right? Actually going to the left. So let me see if I can do it. So in the drawing, I go and change the sign this way, right? I don't have to go back to the calculations. I just change it on the drawing. So I transport these forces to node F, right? Transport, right? I have here the right sign on FFG. I transport these forces to the drawing, and I have it like that. I put the numerical values and I carry these forces to the next node, right? Carry the arrows to the next nodes and I put the numerical value there, right? And I am ready for the next joint. So which joint would you want to tackle next? Node C or node G? Well, at node C I have 1, 2, 3 unknowns, right? 3 unknowns because, well, this guy is known, right? This guy, I forgot to put that there is a known force here equal to 11.3, right? So I have only 3 unknowns, 1, 2, and 3. I cannot use node C. Node G would be the next logical option because I have only 1 and 2 unknowns, right? So which joint next? Well, it appears that we have to choose the one with less or equal than 2 unknowns. So node G is the next option. So the process is exactly the same. Go to the joint, assume some sense on the unknown forces, and then, right, and then solve your equilibrium equations, right? So once you have done that for the remaining nodes, you would obtain this truss, and these are the forces I got, and I have indicated if the force is in tension or compression. And I found two members with 0 forces, right? So this guy and this guy, they appear to carry 0 force. I could remove them from the truss, right? But they carry only a force of 0 under that loading, right? If the loading changes a little bit, these members could carry some load. So it's not a good idea to remove them just because they are 0 force members, right? 0 force members. So method of joints is just about getting reactions and going joint by joint, solving the member, right? For example, in this extra example, I have it here, so you can see the type of supports sometimes books will give you, right? So this guy is actually how the book describes a pin, and this guy is a roller, right? This guy is a roller, right? So this is just here, so you can identify what sort of supports you will have, right, on most books. So here, right, once we solve the truss, right, we calculate the reactions first. So take a moment if you want, pausing the video just to verify that you can get the reactions. And then joint by joint, right, I have joint A here, right, and I have B here, right, and then verify if you can get the same values. Now, a very important concept that you'll use quite a bit is the concept of 0 force members. So what about if just by inspection or just by following certain rules you were able to tell if a member carries a 0 force, right? That will simplify things a bit, right? I would say a lot, because in a given joint, if you cannot apply method of joints because you have 3 unknowns, maybe one of the members is a 0 force member, and then instead of going to a difficult joint, you can actually do the one that you want, right? So yeah, so sometimes trusses will have 0 force members, right? And yeah, they carry 0 force, but they have other purposes, right? Maintaining stability, and then carry other loading arrangements in the future. If the load changes, they actually may not be 0 force members anymore, but carrying some loads, or being able to resist temporary loads during construction, right? So it's a bad idea to remove them in real life, but it's a good idea to be able to identify them, right? So how to do this, right? Because we can save ourselves some work if we identify 0 force members. So there are 2 main situations where 0 force members can be readily identified just by observation, right? In both cases, it is very important. No external load can occur at the joint. Very important, right? there cannot be external loads at the joint. So I'm going to just go back for a little bit and show you the zero force members we got in this truss. And you see, right? You see, there is no force at this joint and there is no force at this joint. There is force in the upper joint, right? So just keep in mind that one of the joints has no load, right? So for the rule to apply, right? Just remember that. So we are here now, right? So these two main cases are the ones that you have to really become good at using, right? The first case is two non-collinear members, right? Two non-collinear members meet at the joint. That's the first case. Two non-collinear members meet at the joint. And three members meet at the joint, right? With two of them being collinear. So let's go to the example, right? This is the first example. Two non-collinear members meet at the joint without external load, right? In this case, the free body diagram will be as shown, and the conclusion must be that both forces are zero. Okay, so what happened, right? So I have two members here. Right? And then if I apply a free body diagram, right, at joint B, right? If I break, well, I can assume the senses of the forces any way I want. If I break this force BC, right, because this is node C and this is node A. If I break this force into components, well, yeah, right? Let me just go back. Yes, this force can be balanced by this force, but who is going to balance this force? There is nothing to balance that force, right? So that situation, that member BC cannot carry any load, right? So this member carries no load, right? And it cannot be that this member carries load because it is connected to a member that carries no load. So this member has to carry also zero load, right? Just because the free body diagram indicates so, right? So this is the first case. There is no load at the joint. You can see node B carries no load, right? Carries no load. The second case is this one. Three members meet at the joint. Two of them are collinear and there is no external load. The free body diagram is shown, right? This is the free body diagram. The conclusion is that the force in the third member is zero. So how can this member be zero, right? So again, right, the breaking down this component, this vector into components gives me one vector like this and one vector like that, right? You could say, right, that force BA is equal to force BD and also to this force, right? You can say that, let's call this guy FBC, let's call it the parallel projection. You can say that FBA is equal to FBD plus FBC parallel projection, right? But then, if there is force in FBC, who is going to carry FBC perpendicular projection? Who is going to carry that one, right? There is nothing. So the only conclusion is that this force in BC is zero, right? This force doesn't exist. It cannot be, right? There is nothing to equilibrate that member. Again, there is no force, external force applied at B, right? So this case was three members meet at the joint, two are collinear, there is no external load. The conclusion is that the force in the third member is zero, right? Now, these definitions are kind of hard to follow, right? Kind of hard to follow, but don't worry, right? It comes with experience, right? Don't feel afraid to go joint by joint, trying to analyze what is going on at the joints, right? Don't be afraid. It's perfectly valid, right? If you miss a zero force member, don't worry. Your equations will, when you apply the method of joints, your equations will tell you that the force the force is actually 0, right? So don't worry about that. The method of joints will give you the answer, right, when you apply it. So let's do a little bit of examples here, right? So let's go, right? Let's try to identify 0 force members in the following cases. So take a look at the truss, right? And I like to go joint by joint. So I start with joint A, no external load. Oh, this is a candidate for that one, right? This is the first case in which two non-collinear members meet at a joint, and there is no external load, right? If you follow the rule, the conclusion is that these guys carry a force equal to 0. So these guys are 0, right? What happened, right? You may say, what happened there? Two non-collinear members meet at a joint, right? Two non-collinear members meet at a joint, and node A has no external load, right? So there is nothing at A, right? So these guys are 0. Other cases, for example, I see here, let's go to node V, two non-collinear members meet at the joint, check, and there is no external load. Oh, okay, here it is. Right? These two guys carry a force of 0. The remainder of the structure, right, is actually, sorry, let's go back. The remainder of the structure is this structure. And then, right, this concept cannot be applied, right? Cannot be applied. For example, if you want to node C, right, you want to analyze node C, there is an external load applied at C, right? What about you want to investigate node B? Well, there is a reaction at B, right? There is external load. There are external loads acting at F, right? What happens at node E, right? At node E, well, you have three members. Then you cannot even apply the one that you have three members. Two of them are collinear, because here we don't have anything that is collinear. So I think we finished. And then we go back to this drawing. We see that, yeah, we got it right. The non-zero members were the ones that we discovered. And this is the shape of the final truss, right? If we remove the 0 force members. So let's take a look at the other example, right, in which we have to see that every time that 3 members meet at a joint, if 2 of them are collinear, the third one is a 0 force member. So what about node D? I see no external loads. I see 2 elements that are collinear. So this guy must have a 0 force. What about node C? Well, I see 2 members that are collinear, this and this. And this guy must be 0 as well, right? What about node B? I see 2 members there, but there is an external load applied here, the reactions. What about node A? Well, I have a reaction here. What about node E? I see a external force, right? So that's it. The surviving elements are these, like these, and these members. And if we take a look at here, down here, we see that yes, that is the solution of my my exercise. I was able to identify the 0 force members. So why is this important? Because sometimes in a given structure, there will be plenty of 0 force members. And then you have to have an efficient way to identify them, right? You don't want to apply the method of joints over and over and over and start becoming worried about some elements because you cannot even apply the method of joints. You have more than 2 unknowns. But some of these members will be 0 force, right? So the first step, one of the first steps at some point, you have to check for 0 force members, because that will make your life so much easier. So that was the method of joints. The next method is a very powerful method known as the method of sections. If we learn this method well, right, you can actually, right, solve systems like this, right? Imagine right? Take a look at how many members there are. What if in the exam I ask you to give me not the force in all the members, but the force in this member? Well, I mean, of course, I'll have loads here. What if in the exam I say, find the force in this member? Well, you go ahead, calculate the reactions, and then start with the method of joints from here, and then you start advancing, right? Advancing towards the member you want to give me, right? And then finally you get it, but you made a mistake here, so all the calculation is wrong when you reach this joint, this member. So the method of sections will give you a tool to investigate in member forces inside the truss, right? Not inside the truss, but just by cutting the truss in a certain position you want, right? You will be able to find forces in members that are well within the truss. Now, this may appear to be, you may laugh at this, but this happened to me when I was an undergrad, right? And then I won't even tell you, I wasn't even a first year, right? I think it was in the fourth year. I forgot my method of joints and my method of sections. And I was forced to do a very long, very painful method of joints, right? Until I reached the member. So I don't want that to happen to you. That's why in the next video, we will study the method of sections. So see you next time. Thank you very much.